we were talking about rates of change, right? We were looking at this example with stopping distance, and I was using that as a opportunity to put my dad hat on and tell you not to drive too fast. Last question on this was interpret the derivative, right? So we found out, and what did we determine here? We determined that the rate of change of stopping distance is significantly higher for, oh, actually, we didn't get that far, did we? We were looking at S of V. The stopping distance at 55 miles per hour was significantly less than the stopping distance at 75 miles per hour. We made the statement that increasing your speed from 55 to 75 means you're only increasing your speed by 36%, but your stopping distance is increasing by 70%. So we can get some pretty good information out of not even the calculus stuff, the pre-calculus stuff, but if we actually look at the calculus stuff, this tells us something else that's maybe a little more nuanced. S prime of V is equal to this function right here. We did the derivative. You guys told me what the answer was. It was 1.4 plus 0.108 V. What is that all about? So if I evaluate this function at 55, what do I get? You guys tell me real quick. What is S prime of 55? Oh, actually, we calculated it, didn't we? Right here. We calculated it. It was 7.34 feet per miles per hour. Okay. At 75 miles per hour, it was 9.5 feet per miles per hour. And I remember we said, okay, this corresponds to a tangent line, right? And because the tangent line is steeper here, the rate at which stopping distance is increasing for a tiny budge in our speed is more aggressive than it is at 55, right? Okay. Now, this is the statement I really wanted to draw your attention to because this is a little bit erroneous. This is how we talk about this in textbooks, and I get why we say this, but it's not strictly speaking correct. And I also want you to see why that's the case. You guys choose which one of these is the correct interpretation of the derivative, keeping in mind that the units of the derivative are feet per miles per hour. A, B, C, or D. Vote with your fingers. 1 for A, 2 for B. What do you think? Yeah. Okay, good. I'm seeing lots of 2s. That's good. It's good. It's 2. That is the answer that they provide. And I can see why they say that, and it kind of makes sense. The derivative represents the additional number of feet needed to stop a car for a 1 mile per hour increase in the speed. Okay, yeah. I mean, that's kind of it, right? It's going to be, you're going to increase your stopping distance budging by a mile per hour. That tells you you'd increase your stopping distance by 7.3 feet when you're traveling at 55, and you'd increase it by a full 9.5 feet when you're traveling 75. Okay, but let's look at the graph on Desmos. I want to show you why that's not totally true. We'll do a little deep dive on the function here a little bit and see what we got going on. So this is the stopping distance function, as a stopping distance as a function of speed. And not surprisingly, it's nonlinear, right? It looks like it's quadratic pointing up, which explains why the tangent lines get steeper as the input number gets bigger, right? For a higher speed, you get a steeper slope, which means that the stopping distance is changing more aggressively, which as you change your speed. Okay, let's look at a couple points here. This was our answer when we plugged in 55. That was our stopping distance, 240. When we plugged in 56, we didn't plug in 56, but if I did, that's our stopping distance. Okay. Now, what if we look at the tangent line? The tangent to the curve at 55 is that blue line. Okay. I want you to see something here. If I zoom in on that, when they described the slope as, when they described the derivative as the additional amount that the stopping distance would change for a 1 mile per hour increase in speed, we can show that that's not totally correct. Where's my other point? I thought I had another point on there. I guess I don't. Here's why. If I focus in on this upper point, the blue line is the tangent line at 55. Notice that it doesn't actually pass through the point at 56. Everybody see that? So if I actually calculate the secant between those 2 points at 55 and 56, I'm going to get a little steeper slope on the secant line than I have on the tangent line, right? So it doesn't actually tell you how much it's going to change, because if I increase my speed by 1 mile per hour, I'm going to get an answer of 7.394, okay? Not 7.34, right? It's a little bit steeper. How come? Well, because the curve is changing. As I move from 55 up to 56, the curve, which is nonlinear, is actually getting a little bit steeper and creeping away from that tangent line. So when people say stuff like that, it's not really correct. It's not really correct. What it's really doing is it's telling us at 55, it tells us the slope. Man, at 55, it tells us the slope of that tangent line, which is just a measure of how aggressively is the stopping distance changing at that one speed for, at that one specific speed, right? Get that? Does that make sense? It's subtle, but there's a little difference there. Okay. No, go away. Okay, so now on to something really important here, life event. Why blowing up a balloon initially seems like it's going to be a piece of cake, but soon becomes tiresome. How come? Because put yourself in that position. You've all been blowing up balloons for some little kid's birthday party, right? And you take that first, and the balloon gets really big. You're thinking, oh, this is a piece of cake. This thing's going to have this thing blown up before no time. But if it's a balloon that gets really big, after a while, when the balloon's pretty big and you blow into the balloon and you don't even see the thing move, right? It hardly even increases. That's kind of a bummer when you get to that point. How come? What's going on? Okay, there's already so much air. Okay, that's what it has to do with the relationship between the volume and the radius, right? Think about this, when we're blowing air into a balloon, as we exhale a lungful of air, what are we directly contributing to the balloon? Volume or radius? Volume, right? Because the volume of air in our lungs is added to the volume in the balloon, right? Okay, so then we want to explore what rate here, what derivative would be interesting to us if we wanted to explore this question. What 2 quantities do we want to relate with a derivative here? Volume and radius, right? Does that make sense? That we're going to want to take a derivative that really we have a couple options. The way it's written right now, I could differentiate this pretty easily and get dV dr equals what? So V is our output variable, R is our input variable. What's the derivative of 4/3 pi r cubed? Four pi r squared, isn't it, right? Because really the 4/3 pi is all just one big constant. I've got the power rule applied to the r cubed. I would just take that exponent r cubed and multiply it by the constant out front. 3 times 4/3 is 4. So I get a 4 pi r squared. Okay. Again, do you notice something? This is not necessarily related, but I think this is just so cool. What is that, by the way? That's a formula for what? Assuming we've got a spherical balloon, what is that a formula for? What does that calculate? 4 pi r. What is it? Surface area. Yeah, it's surface area. Surface area of a balloon, right? That's crazy that the rate of change of volume with respect to radius is equal to the surface area. That will make a lot more sense next year, possibly the year after, when you're taking multivariable calculus. That you're going to look back, so somewhere in the back of your mind, say, oh, Mr. Reuter told me to think about that, and that's going to make sense when you think about it that way. Okay. In a nutshell, what's the only way that the volume could change when we're increasing the radius? Isn't it the surface area that's actually changing, that's being added? Does that make sense? Like if I put, the way you'll think about this in a couple of years is if I had a little balloon, I don't want to get, okay, don't get confused by this. This is way, way extra stuff. But if that's our balloon and we're going to add another breath of air and we're going to expand that out just a tiny amount, right? That's not bad. Yeah. 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 I don't want to brag, but I do make pretty good circles. So the little bit of extra volume that we've added, if I took this extra tiny little shell and I like flattened it out, what would the thickness be? Well, the thickness would be negligible, right? It's really small, but the surface area, if I could somehow, cut this thing in pieces and reform it into a square or something, it's just going to be the area of the surface, right? So there's kind of a logical rationale for that. Again, it'll make way more sense once you guys know about integration, which we're going to learn second half of the year, and when you start looking at multiple variables. Okay, but let's take a look at this relationship. Yeah, we probably can. We can probably take at least most of a day and have a little. There you go, math theme. There you go. Now I'm feeling better about it. Yeah. Well, we'll have to do pi day for sure. Pi day for sure. Okay, so let's look at this graph here of volume as a function of radius. Okay, it's cubic, right? So it's very aggressive. As r increases, the volume starts to increase more and more and more rapidly, and it really explodes upward. So this is not a bad way to think about it, as in order to get the radius to budge out, once the volume gets pretty big, let me stretch this out just a little bit. I know I'm spending a lot of time on this, but this is something that people sometimes struggle with a little bit, and I think it's kind of important. Okay, that's a little better. So yeah, so if we have relatively small volumes, a small increase in radius corresponds to only a small increase in volume, right? Okay. But when the volumes get pretty big up here, a small increase in radius means a pretty substantial increase in volume, right? So to get that small increase in radius, you've got to have a correspondingly large increase in volume. Maybe a better way to explore this might be, instead of calculating dV dr, would be to calculate dr dV. Okay, there's a couple ways we could do that. We could, and then we'll look at those two derivatives and see why one might be preferable to the other. Well, I could just solve this equation for r. Okay, what are the steps to solve that equation for r? If I'm going to isolate the r, what would I do first? Okay, divide by 4/3 pi, which means multiply by 3/4, right? To get rid of the 3/4 or the 4/3, divide by pi. So that's going to give me r by itself equals, really I've got r cubed at this point. R cubed equals 3/4 pi v. And then the last step to get the r by itself, to undo cube rooting, or cubing, sorry, gave it away. Cube root it, sure. Right, so r ends up equaling, it's supposed to be a cube root. Oh, darn cube root of all that stuff, okay? And if I'm taking the cube root of all that stuff, that's really, if I want to write that as a power, well, I could pull the cube root of 3 over 4 pi. That's just a constant. I could pull that out front, right? I could rewrite this as the cube root of 3 over 4 pi times the cube root of v, which is equal to cube root of 3 over 4 pi times v to what power? Cube root is what power? 1/3. Well, if all that is equal to r, well, that looks like a v. Then what would dr dv look like? What's the derivative of v to the 1/3? 1/3, I heard it. V to what power? Negative 2/3. Okay. So cube root of 3 over 4 pi times 1/3 times v to the negative 2/3. Well, that's the same thing as saying the cube root of v on the bottom, right? Okay. So then we could make this whole thing equal to, I'll pull the 1/3 out front because that's not in the radical. And then inside the radical, on the top, we've got a 3. On the bottom, we've got a 4 pi times a v squared, right? Because the cube root of v squared is my v to the negative, cube root of 1 over v squared is the same as v to the negative 2/3. Okay, so there's my dr dv. All right, so now what happens if we look at this graph? The derivative graph really makes this clear. Why blowing up a balloon is so frustrating after a while. If I graph radius as a function of volume, well, that's my graph. That's not surprising though, too, if you think about it. That's the inverse of v of r. Okay? The inverse. When I solve for one variable in terms of the other, really what I'm doing is I'm just expressing that in a way that makes its graph look like it. Now, it's an inverse if the axes are changing. For the red graph, we have r on the horizontal axis and v on the vertical axis. On the blue graph, we flipped it around. So the input variable that goes on the horizontal axis is v, and the output is r. Okay, make sense? And because they're inverses, remember they have that folding symmetry about the line y equals x. Okay, but we won't need to worry about that for a second. Let's just focus on why the blue graph is such a good graph, why that really helps us understand the derivative. For a given radius, or excuse me, for a given volume, the slope gets flatter and flatter and flatter, right? If I'm inputting volume and outputting radius, that means that if the slope is getting flatter and flatter and flatter, like compare these two places. Let me take a picture of this. There and there, how about? We'll look at. Yeah, look what's going on way down here at the start. The slope is really steep, but out here the slope is really shallow of this function. So in here, a small increase in volume gives us a large increase in radius, right? Because down here, dr dv is large. Up here, let's color code this. And let's label these. Remember, on this graph, horizontal axis is volume. vertical axis is radius. Over here, dr dv is small. So small increases in volume lead to, or large increases in volume lead to small increases in radius, right? Because that slope is not very steep. That makes sense? Okay, so the slope of that tangent line, again, tells you how aggressively is the output changing with changes in the input, okay? Big changes in the input here give you small changes in the output. Over here, even small changes in the input give you big changes in the output, okay? Next time you're blowing up balloons, teach the kids something. Tell them why. So, derivative rules. Getting down to nitty gritty here. So what do we know? We know quite a bit of stuff, and I'm going to add a couple others for free. I'm not going to go through the derivations of these. So we know the derivative of a constant is 0. We know that if we're differentiating a sum or a difference, we just differentiate term by term. That's all those are saying. We know our power rule, generalized power rule. And then I'm going to add these other 3 down here. And again, I just don't want to take the time. Maybe if we, at the very end of the year, if we have time for some proofs, we'll come back and prove some of these. But we got plenty of proofs to do. I'm just going to tell you that the derivative of sine equals cosine, and this is a mistake. I got to fix this one right now. Yikes. I got one down here incorrectly. The derivative of cosine x is negative sine x. This is a weird one. The derivative of the exponential function e to the x is e to the x. Think what that means. That's pretty crazy. That's telling you that if you look at the graph of the exponential function e to the x, what's that one look like, by the way? What's an exponential function look like from previous years? You guys would have talked about this a lot last year, I would think. Give you a hint. The point 0, 1 is an important one. What's it do? You remember? E to the x. It's asymptotic on the negative x-axis. It crosses the y-axis at 1, and then it just continues to increase more and more steeply. Think what this tells us. This tells us that if I take any point on the function with the coordinates x, e to the x, what's the slope of the tangent line? E to the x. Yeah, how about that? The tangent, or the slope of the tangent to the curve, is always equal to the value of the function. So the y-coordinate also gives you the slope of the tangent line. That's pretty bizarre. And we get some really interesting behavior out of this function because of that derivative. That, again, you'll kind of get a feel for that as we do more stuff with it. Okay, so those are just ones I'll give you a little handout so you got something on, and I'll post these on Google Classroom. I'll just have in our handout section, I'll just have a continually updating derivative list of the derivatives that you kind of need to know at this point. So here's our derivative list for now. Let's practice this a little bit. So what is the derivative of 3e to the x? What do I do with a constant? Take it out front. Yeah. So I get 3. What's the derivative of e to the x? E to the x. Done. That's it. Okay. No big deal. What's the derivative? Let's try this one. There you go. F prime of x is 2x plus e to the x. Good. How about the bottom one? F prime of x is cosine x minus e to the x. No big deal. See, isn't this easy? Do you like this better than doing those big long limits? I kind of thought you would. Yeah. Okay, so now, next issue. Now, we're not going to finish this today. I just want to kind of set you up for why this is such an important one for us to learn how to do. Oh. And I tell you what, we'll do that tomorrow. Okay, so I'll put I think I've got that assignment up, but we're done with the stuff on power rule and those first kind of preliminary simple derivatives. I'll make sure that assignment